Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 72. So in the previous lecture, we were discussing about the thermodynamic aspects relevant for chemical reactions to occur in the ISM. As part of it, I was talking about some sequence of reactions. Recall, I was talking about this particular reaction, something like A plus B giving something like I1 to I2, and that resulted in some final product. Let's say something like final products, whatever they were, right? So this is what is called as the reactants, I1, I2 and FP. And I want to clarify from the previous lecture because, there were some points I missed, okay? To spell out very clearly, it is that the clarification that when I consider my modulus of delta G, okay, right? Modulus of G, right? The magnitude of G here, this is an increasing order, please note, okay, right? Considering the modulus of G, right? This is an increasing order. And that is why, even though, my I1 could be the species having the maximum absolute value of G, right? It might still not be formed in the ISM. That is the beauty of this lack of absolute thermodynamic control, okay? So this is the first clarification. And but on Earth, right, on Earth, even though, occasionally some of the final products could be formed, right, via a series of molecular collisions, eventually it will all go back to form the thermodynamically most stable product I1. But in the ISM, this can also result in the formation of the final product. That is the beauty of the lack of thermodynamic control as an essential aspect, okay? Please note this. Okay, so this is just a clarification because in the last class, while I was giving you this order, I did not specifically tell you that while considering the magnitude of G, that this is an increasing order. Okay, that is, this has the maximum number associated with it, the maximum positive number vis-a-vis this. Okay, so this was the first clarification. The next clarification is that the entire discussion in the previous lecture was meaningful only under conditions of LTE. What is LTE? Local thermal equilibrium, right? So entire lecture, 71, the one before this, right, was meaningful so I've written here, what I've written here is entire lecture 71, the entirety of lecture 71, okay, right? So lecture 71 is completely meaningful only under local thermal equilibrium conditions, right? Okay. Local thermal equilibrium conditions in the ISM, okay, right? That is important. So, because if, there is no local thermal equilibrium, there is no point in discussing about, some sort of a free energy for this ensemble and the free energy being negative and the excess energy getting transferred, etc., etc. Please note this point. And is it a valid assumption though? Well, it is a valid assumption because we are again talking about the dense molecular clouds where a lot of chemical reactions are happening. Dense and some parts of diffuse molecular clouds. So we're not talking about some crazy situation, such as the temperature being exceptionally high, etc. So in the dense molecular cloud, the LTE assumption is very valid. Okay, so therefore, I'm trying to substantiate that the previous lecture therefore was meaningful. Okay, right? And the content in it is scientific. All right, so please note this. So it's meaningful only under LTE, lecture 71, and LTE valid for a lot of the chemistry that we are discussing. Chemistry in the dense molecular clouds. So please note these points. Okay. So with this, we are all set to begin to the lecture for, begin lecture 72. Okay. So in lecture 72, we shall be discussing about the kinetic aspects, the chemical kinetics relevant to astrochemistry. This topic is a vast ocean. I may not be able to do justice to it in probably one or maybe even 1.5 lectures, but I'll try to illustrate the key points continuing from lectures 9 or 10, right? When I was talking about the difference between ISM and Earth. Okay, so we'll do as much justice as possible in the context of astrochemistry. Now, first of all, how is the rate of a reaction defined? Okay, we'll just see that, because kinetics is all about measuring the rate, right? Some sort of a rate, a rate of a reaction happening, the rate at which a product is getting formed, the rate at which any particular reactant is disappearing, etc., etc. Okay, so for a generic reaction, right, of the form AA plus BB giving CC plus DD, where A, B, C, D are the stoichiometric coefficients, my rate of a reaction, right, I'll just call it small r, denoting rate. Okay, so the rate of a reaction is going to be given by I'll just call, I'll make my life simpler. Okay, right, something like this is equal to 1 by C (1 by D). This can be, generalized irrespective of how many stoichiometric coefficients you have and how many reactants and products you have. The key point is that a rate can be uniquely defined for a chemical reaction. So this is the rate of a chemical reaction. Now, it is expressed either in terms of disappearance of the reactants, which is hence the negative sign, and the fact that, we include the stoichiometric coefficients in the denominator makes it a unique rate. In other words, the rate of a reaction is unique and can be expressed in terms of either the reactants or the products, where my D and the square brackets simply refer to the concentrations. Well, strictly speaking, this should be activity. That is one more definition, but let's not worry about the pedantics and semantics associated with chemical kinetics itself. Overall, the idea is that the rate is unique, right, at a given temperature and pressure. Okay, at given temperature and pressure. Okay, right. So this is the rate of a reaction. This is the introduction to how the rate of a reaction is defined. There's nothing novel about this because pretty much, in high school these days, they teach this idea. Okay, so please note that nothing sophisticated about this yet, other than the idea that, I've told you that this is unique, and that the reason why, the stoichiometric coefficients come in the denominator is to make it unique, so that you can define the rate in terms of any of the species. Okay, that's it. So, having defined the rate of a reaction, the next idea is that there is something called each rate of a reaction, R, can be associated with a parameter called the rate constant. Okay, the rate constant K, denoted by small k. So the rate constant in general, okay, for any reaction, for any chemical reaction, I'll tell you how it is defined. Okay, so notice this. Again, at any given temperature and pressure, let's say that, the rate of any chemical reaction is always proportional to some function of the concentration of the reactants. This is a universal statement, right? As long as I have a chemical reaction, my rate is going to be, some function of the concentration of reactants, right? I don't know the exact form of this expression yet. It is always going to be related to the concentrations in some or the other. Well, it could be linear, it could be, quadratic, it could be exponential, it can also be the sum of the concentrations, it can be anything. I don't know anything about it. That's why I've generically put it as the function of the concentrations of the reactants. Okay. Now, the proportionality constant is what is the rate constant. In other words, my R equals K times function of the concentration of the reactants. What is concentration? Concentration is nothing but some per volume or per mass. Okay, right? Something where I talk about either some moles or some. It can be mass. In the case of gases, it can also be partial pressure, etc. Okay, so that is what is concentration. So the proportionality constant in this expression is what is called as the rate coefficient. Please note this. The next idea we should be looking into is the temperature dependence of the rate coefficient. Now this is once again going back to high school. I'm just giving you a quick recap of this. Therefore, you must have all heard about this equation called as the Arrhenius equation, right? So that is exactly what. So this is how this is the expression via which the rate constant varies with temperature. So here T. Now this is an empirical equation. I want you to note that this is an empirical. Of course, there are more sophisticated versions of this, by introducing more factors, etc. But this is the fundamental equation first proposed. It's called as the Arrhenius equation. And here T is the temperature. My R is the rate constant. EA is what is called as the energy of activation. Notice this. EA, energy of activation. Now, I think we have to go back to probably lectures 9 or 10. I forget which one exactly. Where, I was talking about some kind of an activation barrier, right? I was talking about some kind of an activation barrier for the chemical reactions in the ISM to occur as a kinetic criterion, a criterion via chemical kinetics. Now, this energy of activation can be defined as, in any chemical reaction, it is defined as the energy of the transition state minus the energy of the infinitely separated reactants. Now, go back to lecture 10 or 9, okay, right? Probably, I think, lecture 9, I believe, okay? So, for the exact definitions of what these things mean, okay, the E, TS and E, A plus B, right? Go back to lecture 9 or 10. So there are two homeworks. One is to figure out what lecture it is and then see the exact content. Now, this is not the unique definition of energy of activation. It can always be in terms of energy of A plus B or some other intermediate also. But for the purpose of our discussion, we're going to choose it to be the energy of A plus B. So this is the energy of activation. And this A is what is called as an Arrhenius factor. It's a measure of, one can think about, it's a measure of, the number of collisions that are happening. Recall how do chemical reactions happen? Well, whenever two species collide, right, there is going to be some reorganization, some molecular reorganization due to the energies getting changed, right? The energy states getting changed, and that's how some molecule transforms into some other molecule. So this A is a measure of the collision. Okay. So this is a fundamental equation. There are modifications used to it. So please note this idea that what this equation does is it connects the rate coefficient with the temperature, right, via some collision. Okay, right? An idea of molecular collisions. Now, associated with collision is our next concept. Okay, so associated with collision. See, why is collision important? Because collision is what results in any chemical reaction, right? The collision between, in this case, the different capital A molecules, right? That is what is going to result in the molecular reorganization. So collision is exceptionally important in kinetics. Associated with collision is another term called the collision frequency. Collision frequency, which is given by, let's say, z. I mean, let's say small z. It looks like 2, so I'll rather write this way, okay, z. All right. So the collision frequency is given by, see, for collisions to occur, for molecular collisions to occur, you need 2 species, right? Especially in the interstellar medium, when the number density is very small, we are considering collisions between only two particles, okay, right? You need, let's say, the number of particles present in, let's say, it happens between A and B, 2 species A and B. You need the number of particles A and B present in a given volume, okay, right? So this product Na-Nb is number, I'll say numbers in a given volume. So in other words, it has some kind of a per volume unit, okay, right? Na-Nb is number, so number per volume. So this product together, is some kind of a number density, okay, right? That times you have the area, okay, right, of the cross section. See, when species collide, there is always going to be some cross section of collision, right? So the frequency is also dependent on the collision. So in one formula, I just equate them times the speed with which they collide. Let's say I'll just call this some velocity. We don't care about, I don't use the phrase c, some measure of velocity. Are we clear? Okay, right? So this is one formula. Again, there is no unique formula for the collision frequency, right? One particular formula takes into account the colliding, the number of colliding species in a given volume times the area of the cross section and also the velocity, with which the particles are colliding. Okay, right? So therefore, so with velocity, what are the units? Meter per second. This is going to be, let's say, meter square. If we consider SI unit, and this is going to be per meter cube. So overall, the net unit of this collision frequency is going to be per meter cube times meter square times meter per second, and so all the meters cancel out, so it is per second, and that's why it's a collision frequency. Are we clear? Okay, so it's a measure of how many collisions happen in 1 second. Okay, now this quantity z, right, is very important in astrochemistry. I will give you some numbers. Okay, I'll give you some number to give you an indication of how collisions happen in the ISM. Okay, now for instance, on Earth, okay, if you consider N2 molecules at 300 Kelvin, you're just considering the collision between any two N2 molecules, okay, right? An N2 molecule colliding with another N2 molecule. You again assume LT. To get the Z, you need to make a lot of assumptions. Normal assumptions include local thermal equilibrium. There was an expression from the kinetic theory of gases, which you may have been introduced to in high school, okay, right? So there are various versions of the formula, but this is one prominent version, okay? All right, so if you consider N2 at 300 Kelvin, and let's say at 1 atmosphere pressure, right? So you can use one such formula, right? Some such formula to get a measure of your average collisions, okay? That you can find out your Z to be approximately, I've had some numbers of the order of 5 times 10 to the power 9 per second, right? Please note this, okay? So in 1 second, the number of collisions that's happening is this many. Notice that, how much is that equivalent to, It's effectively equivalent to approximately, you're talking about one collision. If you convert it into nanoseconds, okay, considering this factor, this is one collision happening per, one collision happening per 2 nanoseconds. One collision happening per, no, not 2, it's 0.2 nanoseconds. Yeah. Right? Yeah. So that is how fast, these collisions happen, and that is how many of these collisions happen, right? So this is at 300 Kelvin and 1 atmosphere pressure. Now, in the diffuse clouds, let's say, okay, right? in the diffuse clouds in ISM, let's say at approximately, you even consider, let's say, around like 50 Kelvin or so, right? And at number density, see, the number density here is going to be of the order of 10 to the power 20, okay? At number density is approximately 10 to the power 2 per centimeter cube. And let's say at pressure of close to 10 to the power minus 20 atmosphere, the number of collisions, 5 into 10 to the power minus 8 per second. In other words, we're talking about one collision over approximately 1.5 years. Now, do you understand how sparse the interstellar medium is using this example? I've not done the math because, on the board, I've done it, as part of my work, using some variation of this formula. But this beautifully tells you the distinction between how fast chemical reactions happen in the ISM vis-a-vis how slow they occur. Sorry, how fast the chemical reactions happen on Earth vis-a-vis how slow they can occur in the ISM, right? So this tells you, right? This tells you, it's a beautiful indicator of the sparsity of the ISM, and why I also keep telling you, right? In the ISM, there is a lot of time available. For example, while we were discussing around lecture 9 or 10, in the introductory sections, I told you the time it takes for a chemical reaction to happen in the ISM is of the order of 1,000 or 10,000s of years. That's a lot of time, right? Whereas on Earth, they happen much faster. Well, it all boils down to the physical conditions and the number density. Okay, so that is one fact. And also note, in the ISM, while we were discussing about the notions of electronic transitions, even therein, on Earth, they happen on the order of picoseconds or something. But in the ISM, there's a lot of time for even an electron to go from an upper level to from a lower level to an upper level, right? So the time scale of interstellar processes is something very special, and it happens on a very, very large scale. Are we clear about this? Okay, so that's why the idea of collision frequency is extremely important. Okay, now considering, all these, the collision frequency, the rate coefficient dependence on temperature, etc., what astrochemists have come up with. So considering collisions, the probability of collision, and the temperature dependence of the rate coefficient, etc., some empirical formula. Okay, one empirical formula for the rate coefficients of interstellar reactions. For rate coefficients in interstellar reactions, it is given as follows. It is given by something like the rate constant is given by alpha times T by 300 raised to the power beta times e to the power minus gamma by T, where alpha, beta, gamma are fitted parameters from experimental simulations of the chemical reactions, under very low density, right, under near vacuum conditions, etc., are fitted parameters from experiments and theory. Okay, so please note this. In other words, for the interstellar chemical reactions, we can come up with a formula for the rate coefficients, considering the rate of collisions, the collision frequency, and then the temperature dependence, etc. But it is empirical. I want you to be clear about this aspect. It's empirical. In other words, it is not obtained from first principles. You can just fit some parameters and get this rate coefficient. And by obtaining the rate coefficient, you kind of guess. Okay, you kind of guess how fast will a chemical reaction happen in the ISM, and what is the probability of a species formed via a proposed chemical reaction. Okay, so that is why this equation is useful. All right, so the usefulness of equations such as this, right, is that I'll just call this equation K, right, for weight coefficient. The usefulness such as K is that you can develop, okay, with an equation such as K, one can develop a, a network, right, a network of chemical reactions and their rate constants, which can be proposed as, which may be proposed as the reactions, the meaningful reactions via which molecules are formed in space. So the last sentence, I'm sure you can definitely not read. Okay, so what I've written is, the usefulness of an equation such as this is that one can develop a network of chemical reactions and their rate coefficient, which may be proposed as reactions via which molecules are formed in ISM. So this is molecules are formed in ISM, although it may definitely not look like what I'm saying. Okay, please note this carefully. Via which molecules are formed in ISM. All right, now what is the importance of this? It is that, hey, see, when we say we detect molecules in space, right, we detect them thoroughly, we detect them via experiments, right, but the chemistry, the chemical reactions to which they are occurring, it is a matter of intense speculation. Please know the distinction. Okay, right, it is our job, right, to come up with meaningful chemical reactions which can which are compatible with the fundamental principles of science, right, which don't violate the physical conditions that are present in the ISM, to explain how molecules are formed. Okay, so please note this point. And that is why equations such as this are extremely important. In other words, through this we can propose, one can develop a network of chemical reactions and propose the reactions which are important for interstellar, interstellar molecular evolution. All right. So I want to emphasize once again that molecules detection in space is definitive. Okay, molecules experimental detection, that is a fact. Okay, that is what we spend so much time on even in this course, right? But the reactions via which the molecules are formed in ISM, they are proposed. Okay, right? Why are they only proposed? Because we cannot go and do a chemical reaction there, right? We cannot go to the ISM and perform chemical reactions themselves. All right. So that is why we use the ideas of chemical kinetics, right? We use ideas of chemical kinetics, noting that, the collision frequency has to be very low. We input all the physical parameters that are known to possibly, be representative of conditions in the ISM, and we propose chemical reactions via which the molecules can be formed. What is the advantage of this? With this, we can also propose new molecules for detection, and we can actually understand the chemistry of the ISM and also learn how the chemistry of the ISM, through the chemistry of the ISM, we can learn about molecules, any new behavior on Earth itself. Okay? All right. So on that note, I end this lecture, wherein, we were discussing about the chemical kinetics as relevant to astrochemistry. Now, in the next lecture, we should actually be looking into the chemistry associated with meteorites and planets. Okay, meteorites, asteroids, and planets. Thanks a lot. Have a good day.